Okay, so we're going to be talking about bioenergetics and reactions, and we're going to cover a couple of key topics. We're going to be talking about thermodynamics and the way that that applies to biochemistry. We're going to look at some basic organic chemistry principles that apply, and we're going to talk about how high energy biomolecules allow for group transfer. And then we're going to look at some types of reduced cofactors such as NAD+ and FAD, which serve as electron carriers. So if we think about metabolism as the sum of all chemical reactions in the cell, then really what we're looking at are pathways that produce energy, or the breakdown of molecules, which is going to be catabolism, and then pathways that are using energy to build up complex structures, that's anabolism or biosynthesis. And when we're thinking about these two, the sum of them together are what we think of as metabolic pathways. So if we think of free energy, or the equilibrium constant, this is the ability to measure the equilibrium direction of processes. So does the reaction favor the forward direction, or does it favor the reverse direction? So if you take a look at the K prime equilibrium constant in table 13-2, you can actually see then the relationship between the standard free energy changes of the chemical reactions and the equilibrium process. So remember, when K equilibrium is much greater than 1, then we would expect our delta G prime naught to be negative, and the reaction is going to proceed in the forward direction. When our K prime equilibrium constant is 1, then our delta G prime naught is going to be 0. That means our reaction is at equilibrium. And then when our K equilibrium value is less than 1, our delta G prime naught should be positive, and that means that our reaction is going to proceed in the reverse direction. If we want to look at some examples of, say for our case, the hydrolysis reactions that we see, we can look at the formation of acetate from acetic anhydride. And if we look here, we can see a delta G value of negative 91.1 kilojoules per mole, or negative 21 kcals per mole. If we wanted to look, say, for example, at the elimination of water, so the conversion of malate to fumarate, that would have a delta G prime naught of 3.1 kilojoules per mole, or 0.8 kcals per mole. So you can get a sense of the range of standard free energy changes of some chemical reactions. Notice oxidation reactions with molecular oxygen have very large negative delta Gs. Hydrolysis reactions tend to be strongly favorable, or spontaneous reactions. Isomerization reactions have a smaller free energy change. So usually if we're going between enantiomers, the delta G is going to be equal to 0. And then if we're thinking about the oxidation of reduced compounds, that's strongly favorable. So again, that goes back to that very large, very negative delta G value. So this is actually the way that most chemotropes obtain their energy. And again, when we think about the oxidation of reduced fuels with oxygen, that's always going to be stepwise and controlled. And so it's important to make this distinction that just because something is thermodynamically favorable does not mean that it's the same thing as kinetically favorable. There's a distinction between those two. When we're looking at energetics within the cell, we know that they're not standard if they're not at, right, the standard change in free energy. So if we're looking at actual concentrations of products or reactants, then we're going to look at our Q value. So here, instead of the natural log of K, these concentration values are not at equilibrium, so they'd be Q. And again, we know that our standard free energy changes are going to be additive. So if I have multiple reactions, I can add the sum of the free energy changes. And then the most important thing for us to think about here is the difference between a homolytic and a heterolytic cleavage. It's far more common for us to see heterolytic cleavages in biochemistry, but there are some examples of homolytic cleavage that are relevant. So for example, the formation of radicals. Heterolytic cleavage, typically we see the formation of carbanions, carbocations, or a mixture of carbanions and carbocations. The last thing we're going to talk about here are the idea of nucleophiles and electrophiles in biochemistry. So we have some really beautiful examples that you'll notice look remarkably like the R groups on amino acids. So for example, an O-, this is negatively charged oxygen, which is a beautiful nucleophile. You can see this on a deprotonated hydroxyl group or an ionized carboxylic acid. If we have a negative sulfur, that's the sulfhydryl. We can see that in cysteine. Carbanions are less common, but they are capable of functioning as nucleophiles. Uncharged amines, the deprotonated nitrogen on the imidazole ring, and then of course the hydroxides themselves. And then if you were to compare or contrast that to the electrophiles, say for example the electrophilic carbon in a carbonyl, or a protonated amine group, or the phosphate in a phosphorus group. Or sorry, or a phosphorus in a phosphate group. And then of course the positively charged proton or hydronium. So those are some examples of the molecules that we'll see participating in these reactions. Thanks again, and we'll catch you next time.